I'm Professor Patrick Johnson, and I'm here to talk to you about how to study for Physics 101 and 102 exams. I get a lot of questions throughout semesters saying, like, what is the best way to prepare for an exam? How is it best for me to study along the way, kind of thing. And this is designed to kind of give you a general outline of some good study techniques and ways to best prepare. If you want to talk on an individual basis, I can still talk about that, but this is a way to answer a lot of the questions that I get from a lot of different people. So when it comes to studying, doing problems is the best thing to do. And when it comes to problems, there are kind of three and a half tiers that I like to think of them as. Tier 1 problems are the problems that I base exam problems off of. So when I go to write an exam, I am going to take problems that I've explicitly asked you all to do, whether that's in mastering physics homework, the laboratory activities, recitation in class and homework assignments, and then also problems we do in lecture. That group of problems is where I go to pull from when I write the new exam questions. And so I'm basing what I put on your exam off of that group of questions, which is why I think that these kind of are the kind of top tier questions. And all of these are things that you should have done kind of progressively throughout the time to make sure, like for grades or lecture and in-class recitations are not for a grade, but still I expect that you're doing those problems as we go along. There is kind of what I like to call a tier 1A, which is the practice exam. Now, the practice exam is the exam that I gave last fall or last spring to the equivalent of your class, based mostly off of the same things. Every year, the mastering physics problems change slightly, the lab activities change slightly, lecture questions change a little bit, and recitation problems change a little bit, but the overall content covered is the same. And so seeing the practice exam will give you a sense of kind of what I did with the same material last time I gave an exam on that material. And so it may have been based off of a slightly different combination of problems, but the topics covered are going to be pretty much exactly the same. So you can kind of see what I had done the previous year. The reason why I separated out into a separate group is that, unlike the other problems, which I think are useful for you to do and kind of analyze as you go, maybe look at an answer key here and there as provided, I think the practice exam is best used as kind of a timed activity where you give yourself 2 hours and only an equation sheet. Don't look at the answer key and just try to take it as an exam. And don't worry if you fail it. Like that's why you're practicing, is like so that when you're actually sitting down to take the actual exam, you do better than when you were practicing. And so I think this is most useful as kind of a practice taking the exam. Once you've done it once, you can go back and look at the answer key and compare, figure out what you did wrong, and use it in the other study techniques that I'll talk about later. But the first time through, I recommend that you kind of take it as if it's an actual exam. Now, if you want to do additional problems beyond these, that's where I recommend going to the tier 2 problems. And the tier 2 problems are kind of problems that I've provided to you that I think are good for other reasons. And they come in 3 main categories: the mastering physics practice problem sets, the worked out problems videos, and the worked out problems document. And the mastering physics practice problems are grouped by chapter. And so because mastering physics requires me to set a due date, they're all quote unquote due the week after the final exam, but they're never due, they're not for a grade. They are just problems from the back of the book that I think are useful for one of 3 main reasons. One, they could be useful in that they are problems that could have been assigned as a homework problem, but we just didn't have enough time, or I only assigned 3 problems per assignment, and so I can only assign so many problems overall. And so maybe these are problems that would have been just as good, but just didn't make the cut. The worked out problems videos, I've tried to do a single problem associated with every set of lecture material. And so essentially with each lecture, comes an additional worked out problem. So you should be able to kind of follow along lecture by lecture to see an additional problem for each lecture. And those problems are often, again, things that I would have liked to do in lecture but didn't have time for. And then the worked out problems document is the thing that I've written up, which is going through problems that I think are perfectly good solvable problems that I have typed up fully worked out solutions, which are way more detailed than anything I would expect you all to do. But I want to show you why we are taking the mathematical steps that we're doing. If you are thinking doing all three of these is too much, that's fine. Find the set that works best for the way that you learn. If you like reading, the worked out problems document is the best way to go. If you kind of like watching a video, following along, starting and stopping as you go, that sounds like the worked out problems videos are best for you. If you like kind of a large quantity of problems that give immediate feedback on what you've done, the Mastering Physics practice problems are probably the way to go. But none of these sets are any better or worse than the others, but they are all kind of equally good as far as I'm concerned. And then if you're thinking, well, I've done all of these problems and I'm still looking for more, this is where we get to tier 3, and this is more the Wild West of problems. Tier 3 problems are the rest of the back of the book problems, other textbooks, the internet, Khan Academy, which I have an asterisk on, I'll come back to that in a moment. But these are just kind of problems that I have offered no value judgment on as whether they are good or bad for this class. Some of the back of the book problems go beyond what we do in this class. The internet is a Wild West. You can find just about anything on the internet. Other textbooks, sure, physics is physics, but like maybe it's presented in a different way or in a different order of material. And so sometimes a problem, even if it's from the equivalent chapter, may require physics from other chapters that we just haven't covered yet. Now, Khan Academy has worked out problems that are often very good. The reason I give it an asterisk is it's kind of half into tier 2 because Khan Academy also has videos on concepts, which are very useful to watch and learn concepts from Khan Academy. But as this is more, this tier system is more talking about specific problems that are done. And so going to Khan Academy for problems, most of them are plenty good. But it also can be used as a conceptual resource as well to help you understand what we've been learning all along. So this is kind of where I think you should go to find additional problems to work out. One additional benefit about the Mastering Physics practice problems is that I've also included all of the problems labeled by the book as MCAT prep. And since most of the people in this class are preparing to become doctors, and most of you will have to take an MCAT, this will give you a sense of possible MCAT problems. Admittedly, sometimes those are the problems that require sometimes a different way of doing problems than what we're focusing on in class. We are doing fewer of the problems that are kind of applied to the most realistic of situations, and we're doing more abstracted problems, but I think they're still useful for you to look at for your life beyond this class. So this is kind of where I recommend that you go to find problems. Now, problems aren't the end of the story. Other types of preparations that I think are useful for this exam would be for you to sit down and think to yourself, what are some possible topics that would show up on an exam? Like if I, as a student, am writing a 6-question free response, multiple part question exam, what are the things that I'd ask about? Now, depending on where you are throughout the semester, that list will be different, but just to kind of give you a sense of a list that I came up with for exam 1 material from the first semester, here is a huge list of different topics that we cover. We do 1D kinematics, motion diagrams, position, velocity, acceleration graphs, vectors, 2D kinematics, projectiles. I won't read them all, but like just kind of coming up with just a shotgun blast of as many different topics as you can think of. Some of them are more general, some of them are very specific. Like a banked curve is a specific type of problem that could be uniform or non-uniform circular motion, but just here are some categories of problems. This is by no means a complete list. If you're looking at this and thinking, oh, I would have put this topic, that topic, and the other topic on there, great. But create a list, and then ask yourself, okay, now what would I ask if I were writing this exam? And if I wanted to try to cover as many of these topics as possible, are there any of these topics that I could combine together? For instance, as I just mentioned, banked curves are an example of uniform circular motion. Projectiles are an example of 2D kinematics. Does that mean all 2D kinematics problems are projectiles? No, but that's one way to tie them together. And try to come up with what you think those 6 questions would be. This is also useful to do prior to looking at the practice exam, of come up with your 6 topics and then look at the practice exam and see how many of your topics match up with what was asked last fall. I bet you're going to hit at least 4 of the 6 question types doing that. So think of what you would do, and then kind of group your studying based off of those types of problems that you think would be on an exam if you write it. Now, that being said, just because you think these are the 6 most important topics does not mean those are the 6 topics that will show up on an exam. So definitely study all of the different topics, but kind of prioritize the ones that you think, okay, yeah, this is definitely something I expect to see on an exam. And while you're studying that certain group of problems, it is very useful to go back to the ones that you've done, specifically the ones in the tier 1 problems, but other problems from the other tiers will work just as well for this. And to look at your fully worked out solution and or answer keys and compare and contrast 2 different problems from the same category. See what was different about the problems, what was the same about the problems, and how that affected how you solved it. Now, here I have 2 of my solutions, 2 problems that you've seen in exam 1 material for Physics 101. And they're both projectile problems, and I put up these solutions so that we can look at them and I can show you specifically what I mean by compare and contrast what's going on. So in the first problem, it's a supply plane dropping a package to the Svalbard seed bank, and you have an airplane flying with a horizontal velocity dropping a package from a certain height. This is an object in free fall, and we know how high it's dropped from, its initial velocity, both x and y components, the acceleration, both x and y components, and then we don't know how far it travels horizontally, the final velocities, components, or the time. In this other question, we have a quarterback throwing a football at a 45-degree angle. We know how far it goes. We don't know the initial velocity's magnitude, but we do know the angle that it's thrown at. And because it's a projectile, we also know the components of acceleration and that it starts and ends at the same height. So both of these are projectile problems. So because they're both projectile problems, the first thing I think you should do, as seen in the answer key, is make a list of all the kinematic quantities that you could possibly need for this problem. And then step 2 is where things start to differ. Step 2 is based off of where we know information, where we don't know information. In the first problem, we don't know how far it traveled, but we do know the initial velocities, both x and y component. And so with the first problem, we have 3 of the 5 quantities for the y component stuff. And so we can solve for the time directly, which we can then bring over to the x component stuff to find how far the object traveled horizontally. And so that is how we design that way of solving that problem. We start with the list, and then because we have a 3 of 5, we find the time, bring that over to the x component stuff, and then solve that. With the other question, we don't have 3 of 5 in either list, but we do have the angle of the initial velocity, which allows us to create 2 equations with 2 unknowns, and then use that system of equations to solve for the quantity that we're looking for, which in this case is time. And yes, I only have one part to that second question there, because the other part of the question is a 1D kinematics problem and should be compared and contrasted with 1D kinematics problems. And so in the first problem, we're looking for position. The second problem, we're looking for time. That also affects what we're solving for and how we solve the equations. So this is another area where these 2 problems differ. So I recommend doing this with all different problems and looking at how do 2 problems look the same and how 2 problems look different. And this is important because on an exam, you're going to get a completely new problem. And you're going to have to be able to approach that completely new problem fresh, as if you've never seen this problem. And it's important to be able to look at it and say, hey, this is like the Svalbard problem in this way, that way, or the other way. Or maybe it's like this quarterback throwing a football problem in this way, that way, or the other way. And be able to make those connections to say, okay, even though this isn't the seed bank problem, it's still going to be solved in a way very similar to it because of this, but it's going to differ because maybe in the test problem, we know the time it takes to fall, but not how far it fell. And how would that change the solution? When doing this, I think it's also useful to take a moment to say, what if I changed something about this problem? How would that affect how I solved it? And so thinking about the situation that I just discussed, what would that seed bank problem look like if instead of knowing how high up it was dropped from, if we knew how long it took to hit the ground? We could still find how far it fell during that amount of time because we have 3 pieces of information for the Y component material, but we wouldn't even have to do that to find how far it travels, because if we already know the time, we have the initial velocity's x component, the acceleration's x component, and the time. That's sufficient to answer the question directly. And so that would change that problem quite a bit. It would save us quite a bit of algebra. And this, even if you come up with changing a problem in one way, and then on the exam, I have changed it in a different way, this kind of helps make your brain more elastic. I don't think that's really true neuroscience per se, but like it helps you be able to think about these problems in a more elastic way. And you'll be more prepared for the changes that I've decided to make on the exam. Now, these are all preparation techniques, and this is kind of what you should be doing prior to the exam. I'll highlight a few other techniques that are kind of more amorphous and like harder to give a visual representation of at the end, but let's take a moment to look at what you should do during the exam to maximize your performance on it. And there are a few tips that I like to give for that. The first and foremost is putting something is better than putting down nothing. We have to grade what's on the piece of paper. We unfortunately are not able to read your minds to be able to know what you were thinking. We have to go off of what you have written on the sheet of paper. And so trying something is better than leaving it blank. Leaving it blank will always get you 0 out of however many points for that part. But putting something down can definitely earn you partial credit. The example I always use as the counterexample is if you write, I like spaghetti, I'm sorry, that isn't relevant for what's on the exam. So that still will receive 0 points for that part. So it's not just writing anything will get you partial credit, but if you do something relevant to the problem, you can often get partial credit. Also, unlike anything else you do while practicing, unless you do the practice exam as a actual practice exam, you're never forced to have as explicit time limit to do the problems. And so keeping track of time is important. Now, when I write the exam so that I can sit down and take it in about 20 minutes, give or take a little bit. Now, I have a lot of advantages. I have a PhD. I've been doing this for over a decade. I wrote the exam myself. Like I wrote the questions. So I don't expect that you all would be able to do it in 20 minutes, but I do expect that on average, you all could do it in about 4 times as much time as me, which means it would be about an 80-minute exam, but I give you all 2 hours to do it. And so that still leaves a buffer of time. So even if the average person is taking 80 minutes, that overall it should take 120, like you have 120 minutes to take the exam. So that hopefully will cover everybody for time, but inevitably people are always there at the end. And so like managing your time is important. If you were to break up the 120 minutes amongst the 6 problems, that means you have about 20 minutes per problem. I recommend trying to restrict yourself to 15 minutes per problem so that you have time to go back over and kind of check yourself, because no matter how much you've studied, we all make silly mistakes. And so like checking to make sure you have your units and your correct signs and unit vectors as needed is very important. And taking a moment to go back over your things, you can catch a lot of those mistakes. Probably not all of them, but you've seen me make plenty of mistakes during class and other things. And so we all make them. It's kind of a fact of life. A number of students have talked to me throughout the years about feeling panicked during, before, and after exams. Um, it seems counterintuitive at first, but I have talked to a number of students who say it's very beneficial for them when they're feeling the panicky feelings show up, that they just kind of put their pencil down, close their eyes, and take a few deep breaths and kind of clear their mind. Some students have like asked to go to the use the restroom and just kind of like walked around the hallway for a minute. And like, it may feel like, well, that is 1 out of my 120 minutes that I don't get back. But if you are sitting there panicking, your mind is not in the best space to be able to like focus on the exam and do your best work. And so calming yourself down, clearing your mind as best as you can will really help give you the best performance, even if it takes a minute or two to accomplish that. I find things like this when one of my hobbies is doing crosswords. And like, I find that if I try to work on a crossword and I just can't get anywhere, if I just put it down for a bit, if I come back to it a few minutes later, all of a sudden things that I didn't see are clear to me. And I don't know how that works in your brain, but like it definitely can work. And the number of times that I've seen it work for students in this class, it is very, very useful. Also, when in doubt, ask a question. If you're confused about a thing, ask. If you're not sure how to approach a problem, ask. Now, oftentimes there are questions that we can't answer. So if you say, how do I solve this problem? I will say that's not a thing I can answer. But the worst case scenario out of asking a question is I'll say, I'm sorry, I can't answer that. Or the TA will say, I'm sorry, I can't answer that. We can often help try to clarify the wording of a question, but we can't tell you how to actually do it, or what are the units of this quantity, or how do I do this specific math thing. If you're looking for a trig identity, we're happy to give those to you. But like overall, asking a question never hurts. Like I said, worst case scenario, we'll tell you that we just can't answer that question. And I'll probably say something like, I can't answer that, just go with your gut. And then that's just my way of saying, just make sure to do something rather than leave it blank, because as I said in the first tip, it's better to have something than nothing. Now, going beyond all of this, there are a couple other kind of more amorphous recommendations that I can give. The first of those is really, genuinely speaking, the best advice, but like is very impractical in that it's find what works for you and go with it. I have given a bunch of general tips, but like if you find something else that works for you and none of the other things I say work for you, ignore everything I say and do what works for you. Oftentimes when I'm having this conversation with people, they're looking for what works for them. And so I can offer a bunch of different recommendations and then try them out, see if they work for you, and go with that. The last one that I want to feature is from physics education research, and it shows that it's one of the best ways to study physics. The reason why I put it at the end is not because I'm trying to hide the best study techniques, it's just that it takes more time and like it works best with a partner than it works best if you have a lot of time and a partner. And I know that's not always something that you all as undergrads or postbacks have a lot of extra time laying around. So what is useful to do is take a topic with a friend and then have you tell that friend everything you know about that topic. And that friend kind of just pester you with questions of saying like, well, why is this the case? Why do we know that? Kind of thing, and have you answer their questions. And if you can't answer the question, just say, I don't know, and then make a note on that and then look it up afterwards. But if you also find yourself just regurgitating what you read in the book or what you heard me say in lecture or what you heard Professor Cothran say or your TA say in lab, try to put it into your own words, because taking the concept and then expressing it in your own language is really important for storing it in your brain. I don't know exactly anything about neuroscience, or I don't know if neuroscience even knows exactly why this works, but taking this information and putting it into your own words is a way, to use a kind of physics education jargony thing, it is a way to take ownership of the material in a way that is better than looking at an answer key or watching somebody else solve a problem. And then after you've kind of talked about all the concepts, walk the person through how to solve a problem. Tell them step by step what you should be doing in solving the problem, and have that person ask you, like, well, why am I doing this? Why am I doing that? And then switch roles so that you get to be the one pestering the other person about what's going on. If you can't find the time to do this with a partner, but you do have the time to do it by yourself, you can kind of ask yourself these questions, but it's always more effective having another person kind of going back and forth with you about this. If you want to do this with a tutor, that also works, or one of our TAs, or with me in office hours. I'm happy to do these kinds of things with you as well. But those are kind of the general techniques that I can recommend. Everybody learns on their own way, at their own pace, and I'm happy to work with people individually as needed. But these kind of are the broad strokes kind of recommendations that I offer for success in this class.